Assalamualaikum everyone. So this is our new lecture on the lag compensation. So I will explain how to design this lag compensation. Okay, now so lag compensation, we know that it is used to design to solve or to improve the steady state error. It is same as root blockers. Okay, so the transfer function of the lag compensator is given as this formula. Okay, in this case, this is the gain KC, this is the zeros and poles. So the beta must be greater than 1. Okay, so this is the view of the lag compensation in Bode plot. So again, we know that the function by adding the lag compensator is used to improve the steady state error constant by increasing only the low frequency gain without resulting in the instability. And in this case, we need to increase the phase margin. We need to increase the phase margin to get the desired transient response. Okay, so as shown in this Bode plot, okay, so this is the how uncompensated system look like before we add the lag compensator, and after we add the compensated system will look like this. So again, to sketch the compensated system, we need to consider the desired transient response from the desired phase. So in this case, we will need to find what is new desired phase. Okay, now let's see the procedure how to design the lag compensator. So this is all the procedures. So again, we need to find a new gain K so that we know how to improve, how many steady state error we need to improve. Okay, so then you need to find the gain crossover frequency. Okay, for the gain margin is between 5% to 12% greater, so this is the 5 folds. So usually it takes about 10%, 10 degrees of the new phase margin, and then determine the magnitude. So from we get the frequency gain crossover, then we need to find the magnitude of the frequency, and then sketch or draw the high frequency asymptote. Okay, and then we select the upper break. First we need to find the upper break frequency, okay, to be 1 decade below. Okay, and then we need to draw a straight line of the minus 20 dB slope until it intersect at 0 dB line. Okay, and then find the lower break frequency. Okay, so let's see the example. Okay, so in this example, so given the transfer function of the system, okay, so calculate the steady state error of the system by applying frequency response design technique. Identify appropriate pole of the lag compensator. Okay, so in this case, we need to reduce the steady state error by 5-fold with 10% overshoot, or the correction factor is 10%. Okay, so this is the Bode plot look like when before we add the compensator. So we will get the gain margin minus 45 dB, and the phase margin is minus 75. Okay, so actually in this case the system is unstable. Okay, but we look to design for the compensator. Okay, so now the first solution is we need to find a new gain K. new gain K. So before apply the compensator, when the K is equal to 1, we get the steady state error of 0.01. So it is required to reduce the steady state error by 5-fold. Okay, so meaning that the ESS old ratio to the ESS new is 1 to the ratio of 5. So ESS all we get 0.001. So this is ESS new equal to 1 over 5. So we get ESS new is 0.0002 is here. Okay, so we can find the KV new, which is 5,000. So from the gain or KV new, we will get a new gain K of 5. Okay, so this is the new gain K, which is we need to find from the dot plot. Okay, so when the gain K is 5, so we need to find the starting point for the magnitude. So again, by applying converting the S domain to the J omega, so we will get the starting point at 94 dB. So this is where the new gain K will start, which is at the 94 dB. So you need to draw new line of the gain K in the dot plot. Okay, so this is the magnitude phase of new gain K. Okay, now next we need to find the gain crossover frequency where the phase margin is between 5 degree to 12 degree greater than to yield the desired transient response. So in this case, you need to find the desired transient response. So the system has 10% overshoot. This is the overshoot. Okay, so you can find the damping ratio from the overshoot. And the desired phase margin, we will get, by applying this formula, we will get this one. Okay, so the desired phase margin for compensator, we need to add the correction factor of 10%. So this is the final desired phase margin for the compensator. So from the dot plot, we need to find where this phase margin is located. Okay, so we know that from the phase margin, we will start at minus 180 degree. So you can find by minus 180 degree minus with or plus the 68.51 degree, where it is somewhere in 111.49 degree. So this is the location of the phase margin. Okay, so it is somewhere 111.149 is somewhere here, because this is phase of 45 degree. So 111.49 is somewhere. So this is to yield 68.51 degree. Okay, so it is here. So the gain crossover maximum is something is at 1.05 radian per second. Okay, so next, okay, find the frequency, determine the magnitude of the system at the frequency found. So from the dot plot, the magnitude of the system is, okay, you must project the at new gain K. So it is about 74 dB. So this is the new gain, new magnitude phase. Okay, so we get the new gain margin. Okay, so next, in order to sketch the compensator, so you need to find the upper break frequency. It is to be 1 decade below the frequency of WGCO. So we find this from the word plot, and you need to find 1 decade below, so you need to multiply with 0.1. So the higher the upper break frequency is about here, and okay, so this is the high frequency asymptote. So upper break frequency is somewhere here. So for this is the dot plot for compensator. Okay, so in this case, as it has a very low scale of the frequency, we need to use for 1 decade. This is for 1 decade, 0.1 and 0.01, because it is as a low frequency scale. So this is some upper frequency with somewhere here 0.10 radian per second. Okay, so we need to, then from the intersection of the upper frequency, so we need to draw a straight line of minus 20 dB slope until it intersects with 0 dB line. So what you need to do is you sketch from the upper break frequency, you need to sketch minus 20 dB per decade. Minus 20 dB per decade is somewhere here to here. So this is 74 and this is 64. Okay, and you sketch up until it intersects at 0 dB line. So you will get the lower frequency is, so you will get the zero frequency is at somewhere at 0.000019 radian per second. Okay, so this is the compensator. So next, to find the gain of the compensator, so we use the formula. We find the gain. We find the lower break frequency omega L. This one divided by the upper break frequency 0.01. So this is the transfer function of the gain capacitor, the lag compensator. So this is what we need to find, or we design for the gain compensator. So this is the final system of the lag compensator. So that's all for lag compensator. Thank you.